I'm going to make sure that my like throughout background noise thing is okay. It's selected. My son's practicing piano. They're leaving soon. I heard him say, "Mom said I'm supposed to practice piano," which is true. Just terrible timing. But that's okay. So anyway, I'm going to give you a rundown though of numerical integration. I'm not going to expect tons of you. It's going to be 13 homework problems. Once I modified them, I went through and made sure that they still worked appropriately because all I did was remove parts. I made sure that the points were still allocating the way they were supposed to be. And then once I finally got done with it, I went to go assign it and it like refused to assign. I finally got it to work like 2 hours ago. So it's been kind of nuts with this section, the way that it is done here. But I didn't want you getting into issues with your decimal approximations and being like, okay, well, it's not accepting my answer. And it really wasn't anything to do with entering decimal answers themselves. All the approximations I got to work just fine. It was using approximations mid-calculation to find error. So I'm just eliminating that issue altogether. I'm not going to ask you about error. So if you're looking at your homework problems from your book and you're trying to do those for whatever reason, if you wanted extra practice, they might ask you to find error in the approximation. I'm not going to ask you to do that on the homework, and I'm not going to ask you to do that on the test. I'm just going to ask you to use either the midpoint rule, the trapezoidal rule, or Simpson's rule to approximate the integral. I'm not going to ask you about error. I'm pretty sure there's no error left in there. Even in the explanations, I took it out because I didn't want it to be confusing. So I kind of just wanted to go over that tonight. Now, technically, I was planning on doing 7-6 and 7-8 all tonight, but I think I'll do 7-8 asynchronously. It's not going to take very long to record, just because I ended up switching my table of integrals at the last minute, and because I spent so long doing this numerical integration thing, I didn't recorrelate everything with the table that is used in Sullivan. Last time I used a different table, and I didn't want to use a different table because I wanted to use the table that you guys had in your book. So, by the way, I am going to be, I don't have to share this, I guess. I am going to be telling you in the asynchronous video, which is going to be very short. I mean, think like 30 minutes. I am going to be directing you to the table of integrals that I'm placing on D2L. I already put it up there. It's in the content section. I'm going to actually share that with you just so that you know exactly which one I'm talking about. Yes, that should be it. Okay. So you guys should be seeing my D2L tab. Okay, so this is the content section in D2L. So there used to be something called derivatives and integrals. I just renamed it basic derivatives and integrals. This is just that sheet that I called like a cheat sheet. It doesn't come from the Sullivan book because the Sullivan book didn't have a good variation on this. So I had pulled this from a different text that I used to use years ago. This is not a very comprehensive list. It's basically, it's just the basic ones that you're allowed to use formulas for. Anything else, we would be using some sort of integration process for that you learned in this section. But these are just the basic ones and then basic derivatives. What I added today in handouts and formula sheets in the content section was the table of derivatives and table of integrals. Now, this is actually in the back of your Sullivan book. It's in the way, way back. I don't know if anybody even has a paper copy. It should also be available in the ebook in the back. I could probably look at that right now. Wait. Let me look at it real quick. Might as well look at it with you, right? All right, so I'm in my ebook right now. Appendices and tables. It should be under tables. Table of derivatives, table of integrals. So the table that I put on D2L should be the exact same as this table. If you see any discrepancies, let me know. There was an issue with WebAssign last semester where they had a different table than your book had, which was really confusing, and it didn't really make a difference for the integration, but there was one integral where something was funny about it. I can't remember exactly what it was, but these should all be the same number-wise. as the ones in your book. I'm going to look at them really quickly, but these are the ones that we're going to be looking at in 7.8. So it starts with, let's see, basic table of integrals, basic x to the a. Okay, number 12 is tangent, fine. Yeah, and then they just sort of have different types of integrals. So integrals involving a plus bx, a squared minus x squared. So this is the kind of thing that, you know, if normally, for instance, if you're looking at something like, I don't know, 34, maybe you would have tried to do partial fractions or like a trig substitution on that. In 7.8, you're going to be using tables. So I'm going to explain all that when I go through the asynchronous with you. But the tables are only supposed to be used when I specify on the exam. So I just want to make sure that you understand the tables that I'm referring to. They're accessible in the ebook, which is where I am now, but they should be the exact same. They go up to 135. Let's make sure they do that in the book also. Yes, they do. I won't give you any hyperbolics. But yeah, so these are the exact same as the ones on D2L. So, and D2L, they look exactly the same way they do in your book. But they also will go up to 135. All the numbers will be the same. So when I'm going through your asynchronous lecture, I'm not going to have more than probably like 4 examples for you. But when I refer to the table and I say, okay, I'm using formula number and whatever number I'm using, these are the tables that I'm referring to, these ones that you're seeing on D2L. So I put those up there for you. I was going to go through it in class tonight, but I think I'm just going to do it asynchronously. Like I said, it'll be half an hour or so. And I think I'll just get you out of here a little bit early tonight just because I had such a ridiculous time putting all this approximation stuff together. So I ended up sort of cutting my lecture short a little bit since I didn't need to go through all the derivatives for finding maximum values for the errors. It made the problems actually a lot easier. So you're lucky that I was having these achieve issues. So numerical integration will not be that hard for you now. There are some semesters I don't even get to numerical integration. I am doing it this semester because I feel like we have the time and it was already put on the schedule for us. We're actually doing pretty well schedule-wise. Now, that being said, what I was supposed to do was finish the chapter tonight, and then on Monday, you were supposed to, by Monday, have watched an asynchronous lecture on section 8.1. However, I had a feeling that you might not get to that before your test on Wednesday, and then you would have another asynchronous lecture to watch after that on 8.2. And I didn't want to have everything introduced to you asynchronously and have all of that basically you'd be doing after your test. I thought that seemed like a lot. And I also put up an extra homework assignment for you from 7.9. 7.9 is mixed practice, where you're working on all different types of integrals that are mixed together. You have to figure out the best way to go about solving them, not using tables. So that's going to be more work that you're going to be doing on this chapter that's not necessarily something I'm teaching you, because it's more of just a review and everything's sort of being pulled in together. So that's kind of why I decided to just do a short asynchronous lecture on tables of integration, which I will have up for you by Friday. But that will also be included on your test Wednesday. Like I said, it's going to be really short. I'm not going to put anything super crazy on there where you're going to have to fit it to a table. It's going to be pretty straightforward. And like I said, you're only going to be allowed to use the tables on your exam when I specify use the table of integrals. And I'm even going to state, tell me which number formula you used. So if you're looking at these formulas that I have up here, like for instance, I just said I wasn't going to give you any hyperbolics, but I could give you something like dx over x ln x, and then you would tell me that you used formula number 119. So if I say use a formula, even if you can think of another way to do it, I mean, feel free to do it another way and check it, but you'll be using a table when I specify. Okay, so that's my plan heading into the test next week. Your test is on Wednesday during our normal class time. I know we've only had one test so far, so we have a pretty small class. It shouldn't be a huge deal to get everybody checked in and ready. Make sure that you have 2 viewing angles if I can't see your hands, and at least 2 corners of your screen and at least some of your face, and the 1 angle that you have. Sometimes students will give me an angle that's sort of like off to the side, and that's the best because usually in that case I can get only 1 viewing angle and I can see enough. I can see your profile, I can see part of your computer screen, I can see your hands, I can see your workstation. It's really important that I can see your workstation. So work on that if you had trouble with it last time, just so that you're ready. This test usually goes much more smoothly than test 1, just because the material is a little bit more straightforward. And it's a little bit easier to get partial credit on these because you're not so focused on setup. It's more about like, are you actually just performing the middle work correctly? So that's all right, that's the plan. So you have an assignment up already from 7-9. I don't know if any of you started it. I totally forgot to look. But you do have that assignment up there that's available for you. It will be due Wednesday. The other assignment that you have up there is for the test 2 review. It says in the title that it's optional. That means it's available to you if you feel like you'd like some more review. I do feel that once you work on 7-9, that will be a good enough review for you. The only difference is that the test 2 review also includes, I think, 2 L'Hopital's rule exercises and an improper integral. So it just sort of meshes everything together. Maybe not an integration table, but you'll have a separate assignment for that. Okay, so your test is next week, Wednesday, so the 20th, it's a week from tonight, our normal class time. You'll have the full class time to do it from 6 to 8:20. Make sure that you have your viewing angles set up. Make sure everything's charged. I think that was it. Jenny, do you have a question?
Oh, yeah. So for when we did like 7.7, you know how you like pulled up the graph on our graphing calculator so we can look at it? Are we allowed to use Desmos to pull up the graph too during the test?
Yes, you can do
Okay.
that.
Okay, yeah, because it's just easier to see when it's on like your laptop screen.
Yes, that's fine. I know the Desmos calculator is actually a little bit more user-friendly for most things than your TI, I think. I hate to say that, but I mean, especially since you can graph graphs that aren't functions too, which you can't really do on your TI without manipulation. Yeah, that's fine. You can use Desmos. Good question. Anyone else? Questions about the plan or heading into next week or anything like that? I have not yet gotten an email about make sure you enter your midterm grades. I'm sure it's coming very soon though, because we're mid-October at this point. I'll probably get one soon saying to put them up by like Monday at 7 p.m. If not, hopefully I'll get your test graded before the midterm grades are actually due. I don't remember what the actual midterm date of our class is. I have it written down somewhere. But the midterm grade is due like a week after the midterm date, I think. So it would be awesome if we had a second test score in there. But we might be a few days shy of that. What else was I going to say? Oh yeah. So the only other thing I guess I was going to say was you're going to have your test Wednesday, and then I will have an asynchronous lecture ready for you, ready to go after your test, so that you can start on 8.1 and maybe a little bit of 8.2. We'll kind of see how it goes. How was the quiz? I don't know why I'm asking. What am I expecting to hear? That was another thing that took excessive amounts of my time today. I just had to keep rewriting every problem. It wouldn't let me edit anything. It would let me edit it, and then it just wouldn't save it. I'm like, oh, I guess I have to rewrite every problem that I want to edit at all. I almost didn't give you a quiz. I was almost just like, you know what, we're done here. But in the end, I persevered, and you got your quiz, which it looks like some of you needed some of those scores. Not everybody, but wonderful. Does anyone want to talk about the quiz, or do we feel okay about it? Are there any other questions before I start talking about numerical integration and approximation of integrals? Okay. Wonderful. Then I'm going to go ahead and get started. Like I said, I don't think this will take the whole time. I know famous last words, right? I'll say that and then we'll end up saying till the way end, but I don't think that's going to be the case. I really just want you to focus on preparing for your next test without being bogged down. You know, some weeks are just super crazy where there's just so much that you feel like you have to do, and then other weeks are a little bit more focusing on just pulling things together. Okay, so numerical integration is section 7.6. I think when I put your assignment into Achieve, I think I put it in as like a integration approximation or something like that. But what we're going to be doing in this section is basically approximating integrals. So that's what I put it in as, approximating integrals. So sorry if that's confusing. I couldn't remember on the fly exactly what your book called it. Oh no, they do call it approximating integrals. I have too many calc books in front of me. I was trying to find you guys some really nice pictures, so I was pulling out a bunch of books. Okay, so we're going to be looking at 3 different formulas here for approximating integrals. Now, you might be wondering why you would want to approximate an integral. I know, I would be wondering that too, because I spend so much time telling you guys to leave your answers exact and how I don't want an approximation. However, sometimes, as I mean, you can see now that we're at the end of the chapter, sometimes you get to an integral that you just don't know how to solve. Or maybe you don't need the answer to be exact. Maybe you just want to get somewhere close. And that's what this section is for. Just getting an idea of what the value of the integral is without actually having to find the exact value of the integral. So I'm going to give you 3 different rules, and each one uses a different technique. The first one that we're going to talk about is the, let's pick one. We'll talk first about the trapezoidal rule. That's probably the easiest of the 3. And maybe, well, let's talk about midpoint. I think midpoint's a good place to start because I feel like that has more ties to what you thought about more in Calc 1. Let's do the midpoint rule first. Okay, so I'm going to give you the rule, and then I pulled up some nice pictures from one of my other texts that I'm going to show you. Your book has some decent pictures. Just for some rules, I thought their pictures were better than others. If function f is continuous on the closed interval from a to b, then the integral from a to b of f of x dx can be approximated using the following formula. Now, this formula is going to include some other pieces that I'm also going to have to define for you. So just hang in there, and you'll have it all in just a minute. The first factor is going to be b minus a over n. And we're going to take that factor and we're going to multiply it by a quantity. Now, that quantity is going to vary based on how many subintervals you're splitting your curve up into. So we're going to start by taking the value of f evaluated at x sub 1 bar. And like I said, I'm going to remind you of what x sub 1 bar is. You've talked about bars before in math, maybe more in statistics. You're going to add that to the value of f of x sub 2 bar. And you're going to go on through your interval all the way up until the second to last term. the n minus 1th term, and then you'll go up to the nth term. So this is the formula that you're going to use. Of course, we're kind of going to be focused on what n is because you're going to want to need to know what you're dividing by. Not only that, but also how many terms are going to be inside this factor. So x sub I bar is going to be equal to x sub I minus 1 plus x sub I divided by 2. So it's going to be the average of the first two data points. So of course, I is going to be from 1 to n. And the closed interval from A to B is partitioned into n subintervals. Subintervals is technically one word. I should not, it's technically not hyphenated, but I hyphenated it, but that's all right. The subintervals are going to go from x sub naught to x sub 1, and then they're going to go from x sub 1 to x sub 2, so on and so forth until you get to go from x sub n minus 1 to x sub n. And each one has the same width. The width is going to be delta x, and that's going to be b minus a over n. Now, you may or may not use this delta x equals b minus a over n. It kind of depends, I think, on what values you're given. Some of these are going to be really easy to split up and divide into parts. Others, especially anytime you're working on a trig function or looking at some sort of weird fractions of pi, you might want to use this just to be sure about what values you're getting when you split your interval up into parts. So let me show you a picture of the midpoint rule. I knew I had this somewhere and I can't find it until I'm going to turn this up over. Hold on. You were working on your quiz. I finally found it. Nope, this side. There we go. I'll zoom it in a little bit more for you. So what the midpoint rule is doing is it's setting up rectangles, sort of like what you initially learned to do in Calc 1 when you were thinking about integration as being the area underneath the curve. We didn't go too deep into actually computing the areas using subintervals in my class, but I definitely gave you like a basic overview of what we were doing when we were integrating. So we're looking at the area under a curve when we're integrating from A to B. So starting at your left endpoint A and heading over to your right endpoint B. And what you're doing is you're splitting this up into these n subintervals. Now, n will just be how many rectangles you have in this case. It's called the midpoint rule because you're going to be looking at the height of each rectangle as it hits the curve. So you're going to be looking at that center value in between these two partition points. So when you split this up, your first rectangle, for instance, goes from A to x sub 1, and then you're going from x sub 1 to x sub 2. The midpoints are just going to be the halfway points of these rectangles where you're looking at that on the curve, just so that you can ensure that you're equidistant as you work your way through. But that's basically what this rule is doing. It's just using rectangles. Like I said, each one of these rules is going to be using a different sort of geometric process in order to evaluate the approximations. But this is what we're going to be doing. So not only are we going to be partitioning this into these n subintervals, but in our case, we're also going to be splitting those in half to get the midpoint values. So we'll be taking the, the x sub 1 minus A, whatever that is, and then splitting that in half to get the first midpoint. So that would be that x sub 1 bar here. So this book calls it m sub 1. Our book calls it x bar sub 1, but it's the same idea. So if you want to think about it as m sub 1 because you don't like the bars, you can think about it that way too. But this is midpoint 1, midpoint 2 as you work your way through instead of saying x bar sub 1, x bar sub 2. But it's the same idea. That's what those are. Before I take this picture down, does anybody have a question about the picture or how this might relate to the approximation formula that I gave you or any piece that's missing? Obviously, I'm going to give you an example. Okay. Wonderful. Okay. Oh, one more thing I wanted to mention, just like you talked about in Calc 1, the whole idea is you're going to get a closer approximation depending on how many subintervals you split this into. So for instance, if you only split this into n equals 2 subintervals, you'd only have 2 rectangles. So one would go from A to that midpoint, and then the other one would go from the midpoint over to B, and you would not get a very close approximation. You'd basically just be looking at the average of this value, for instance, and that one. The further you split this up, the more rectangles you get, the better of an approximation you're going to get because you're going to have less empty space in between the curve and the rectangles, and then less, extraneous space above. Okay, let me flip this back around. Zoom you back out. Okay, so I'm going to give you an example using the midpoint rule. And I'm even going to give you the exact value of the integral, and we'll kind of compare what happens as we break this down into different subintervals. Okay, so let's see. Example 1. I want my directions to match so that you know exactly what you're doing. Use the midpoint rule to approximate the integral. Use the midpoint rule to approximate. And then I'm going to go ahead and give you the integral. We're going to use the integral from 2 to 3 of 1 over ln x dx. And we're going to look at 2 different values for n. I'm only going to do that for this example because the examples that you're going to be asked to do for homework are only going to ask you for 1 value of n. But I want to be able to, at least for this first example, to compare the different values of n so that you can sort of see how you get closer to that exact value. And it also gives you some practice using the midpoint rule. So we're going to do this for n equals 3 and n equals 5. And like I said, we're not going to be talking about the error because I already explained that. I don't even want to get back into it again. It was driving me crazy. So I'm going to, oh, you know what? I do want to have my formula up here. But we are going from 2 to 3. I'm going to have to go back for my formula here. Let's first talk about n equals 3. We'll focus on that first, and then we'll talk about n equals 5. What I like to do is, since I know I'm going to be splitting this up into these little subintervals, first 3 of them and then 5 of them, I kind of just like to go from A to B and just visualize what's happening in between. I'm not going to be graphing this function. I'm just going to be thinking about what's happening on the x-axis of the function. So if I'm going from 2 to 3, then 2 is going to be my value for x sub naught. And then 3 is going to be my value for x sub 3. That's going to be my third data point. And what I need here is I need 3 subintervals. The number of subintervals you have minus 1 will be the number of tick marks that you need to split this up. So for instance, if I want to split this into 3 different subintervals, then I need to put 2 tick marks in here to split it up. So now you can see that I have a subinterval from 2 to the first tick mark, and then from the first tick mark to the second, and then from the second to that last value that we have. So if our first value is x sub naught, my second value is going to be x sub 1, and the one after that will be x sub 2. So what you need to determine at this point now is what these values are actually going to be. And one way that you can do that is just by sort of eyeballing it or using your arithmetic, because you know that in order to get from 1 to the next, I mean, you're basically covering a span of 1, and it's split up into 3. So these are 1/3 apart in each case. But you can also use this formula that I gave you for delta x equals b minus a over n, and this will tell you what you need to add to get from one piece to the next. So we can say that if delta x is b minus a over n, then our delta x, or how much we have to move to get from one point to the next, is going to be, well, b minus a is going to be 3 minus 2. Those are just the upper and lower limits of integration. And then n in this first instance is 3. So I'm going to divide that by 3. So 3 minus 2 is 1. Divide that by 3, and you get 1/3. What that means is all we need to do to get from one data point to the next is add 1/3 to it. So really, this is going to be your first data point plus 1/3. Now, if I were you, you don't want to end up with an answer that's off with your decimal approximation. I would leave this as a fraction if you can't make it a terminating decimal. So for instance, 2 plus 1/3 would be 2.3 repeating. You don't want to write it as 2.33 because you're not going to get close enough to that exact decimal value. So if I were you, I would just write that as a fraction. So 2 and 1/3, well, 2 times 3 is 6, plus 1 is 7. You'll get up to 7/3. And then add another third, 7/3 plus 1/3 gets you to 8/3. And then you can always double check that 8/3 plus 8/3 plus 1/3 gets you to 9/3, which simplifies to 3. Sometimes I even automatically just put common denominators on my endpoints, and then I sort of just look at what the numerators would have to be. So for instance, I might write 2 as being 6/3, and then I would write 3 as being 9/3, and then I can just look at my numerators and go, okay, I have 6, 7, 8, 9. Perfect. But these are going to be the values that we have for x sub naught, x sub 1, x sub 2, and x sub 3. So once you get going on this and you get into a sort of a rhythm, this will not be too confusing. I think when you first see it and you're trying to put it all together, it takes a little bit of, figuring out where everything goes. But after that, I think it's pretty smooth sailing. Okay. So we have these values for our x sub whatever numbers they are. What we need for our formula, going back up to our midpoint formula, is we need function values evaluated at the x bars. So these would be like the average values between the values. Now, I gave you a formula for how to find these, but basically what this formula is stating is that if I want to find x sub 1 bar, then I need to take x sub 0 plus x sub 1 and divide it by 2. And I can do the same thing to find the middle value in each subinterval. This is another thing that some of you who are just mentally quick with your arithmetic might do without even using the formula. But I'm going to show you how to use the formula here. Okay, so I know that x sub 1 bar is going to be x sub naught bar, x sub naught, not bar, x sub naught plus x sub 1 divided by 2. And that's just using this formula that I put for you up here. So the x sub I minus 1 is x sub 0 in this case. Add x sub 1, divide by 2. So your x sub 0 is 2. Your x sub 1 is 7/3. and you'll divide by 2. And some of this is, most of what you're doing here for approximating these integrals is just going to be some busy work with your arithmetic. And you can even do a lot of this in your calculator, but I know that 2 is 6/3. When you add 6/3 and 7/3, you get 13/3. When you divide by 2, you're multiplying by a half. So this gives you 13/6. If you're doing this in your calculator, I know this seems like a really ridiculous comment, but I'm going to go over it anyway, just because we sometimes make silly mistakes, and I just want to remind you. When you're actually computing this, make sure that if you're adding this in your calculator, you're putting parentheses around your numerator before you divide it by 2. So you're doing 2 plus the fraction 7/3 in parentheses, then divide it by 2, then math and enter to get your fraction of 13/6. Okay, now this is a lot of this intermediate work. I don't need to see every little piece. If you just wrote x sub 1 bar equals, and then, I don't know, this maybe, and then that, these two would be fine. But honestly, if you're just eyeballing this and you said, okay, well, this must be 12/6 and this must be 14/6, what has to be between them? 13/6. You can do that too. I mean, 6/3 is 12/6. 7/3 is 14/6. So the difference between 12 and 14 is 13. And that's where you get this x sub 1 bar, which is going to be 13/6. I don't want to add too much here because the surf looks so crazy and there's already a lot going on. Okay, so that's sort of just the busy work that we're doing in between here. So we don't need a whole lot more here. We found already that first midpoint. Now we need the second midpoint and the last midpoint. So x sub 2 bar is going to be x sub 1 plus x sub 2 divided by 2. So that's 7/3 plus 8/3 divided by 2, which is going to be 15/6. And then the last one will be x sub 2 plus x sub 3 divided by 2, not 3. And you will get 8/3 plus 9/3 over 2 is going to be 17/6. I mean, show me that you're doing the work, but I don't need to see every little teeny tiny thing. Okay, so we're getting close to the point where we're actually going to be able to evaluate the integral. Let's go back to our formula. Sorry, I might have pushed that up a little too quickly. The last thing we need before we can start to plug this into our calculators is the function value at our x bars. So we need f of x sub 1 bar, f of x sub 2 bar, and f of x sub 3 bar. So we're going to get those next. Now, because this particular function is 1 over the natural log of x, we can't really evaluate this to much of anything simpler. So when we evaluate f of x sub 1 bar, we're just going to be taking 1 over ln 13/6. I'm basically just writing this down at this point because it's not like there's a trig function where we can evaluate it at pi over 2 or pi and there's anything we can simplify. This is basically going to go straight into our formula. So I'm really just kind of outlining the pieces that are going into the formula at this point. F of x sub 2 bar is going to be 1 over ln 15/6. And then f of x sub 3 bar is going to be 1 over ln 17/6. I know this lesson is not nearly as exciting as some of the integration techniques that we covered earlier in the chapter, but hopefully it'll be sort of a breather for most of you. Usually this stuff on the test goes really, really well, just because just popping numbers into formulas. I mean, there's a lot of in-between stuff, but it's nothing that's super crazy. Okay, before I put this into the formula, are there any questions on any of the pieces that we have put together so far for the integral? Okay, and by the way, this is the only formula that's going to be using these midpoints where you're going to have to find the average between these sub-values. So the other ones, I feel like even though I'm giving this one to you first, it's maybe a little bit more complicated than the other ones. Okay, so I'm going back to my formula now. Put it up here. So what I'm looking for is b minus a over n. So I'm going to go from, let's see, I'm going from 2 to 3 of 1 over ln x dx. Right, okay. This is going to be approximately equal to b minus a over n. Well, you already computed that value, so you might as well put in the simplified variation. B minus a over n, we found to be 1/3. So we're going to put that into the formula as is. So b minus a over n is 1/3. And we're going to multiply this by our function value evaluated at x sub 1 bar, which is 1 over ln 13/6 plus 1 over ln 15/6 plus 1 over ln 17/6. And that's it, because all we're doing is we're taking this up to f of x sub n bar. And this was x sub n, remember n was 3, so x sub n bar inside of our function gave us this quantity. Now, honestly, the other hard part here is just putting this into our calculator appropriately so that we don't miss a parenthesis or accidentally do an improper order of operations. But this is the quantity that we're putting into our calculators. So I'm going to show you the way that I'm entering this in my crazy light, because that's what goes on here now. I'm going with 1/3 times, and now I'm opening my parenthesis, and anything else is going inside this parenthesis, and I need to make a mental note of that. 1 divided by ln 13/6. Now, when I put the 13/6 into my natural log, I need to make sure I close off that parenthesis, because I don't want that to accidentally get a +1 inside the logarithm. So my next term is +1 divided by ln 15/6. Don't forget to close off your parenthesis. And then we're going +1 divided by ln 17/6. Now, when you close off the parenthesis for your natural log, don't forget, this is also your last term. You need to close off the parenthesis because that entire quantity is getting multiplied by 1/3. So if you want to go back to the beginning and just make sure you didn't miss anything and go through and look at it, 1/3, don't put in 0.33 because that's not the same as 1/3, and you don't want to end up getting some weird approximation that doesn't actually get you close enough to the actual approximation. All right, so you closed off this parenthesis, that's good. You closed off this one, that's good. And that one is closed off, and then your entire factor is closed off. So when you hit enter, you get to 1.114965389. Now, Achieve is going to ask you, of course, to round that off. So this is what your calculator is giving you. Be careful with your rounding, because in this case, for instance, usually Achieve asks you for 4 decimal places. And you'd be surprised how many calc students have trouble rounding something like this. The fourth decimal place is this one. The number to the right of that is a 6, which means that the 9 goes up by 1, which means that the 4 also has to go up by 1. So if you're rounding this to 4 decimal places, it's going to be 1.1150. And that's what you would enter in Achieve. So just pay attention to the rounding instructions. They should not change from example to example, but they might. My math lab sometimes does that, and students get used to rounding to a certain number of decimal places, and then they'll do it for another problem, and it keeps telling their answers wrong. And they're like, why is my answer wrong? I'm like, well, you didn't round to the correct number of decimal places. And then they'll tell me like, oh, they changed it up on me. These problems are all newer, so they should be a little more consistent. Okay. We are also supposed to discuss this integral for n equals 5. Before I do that, does anyone have a question on the approximation we did for n equals 3?
Nope.
Okay. Okay. So now we'll do n equals 5. Now do n equals. These instructions are just so precise. Now do n equals 5. Okay, so when we're splitting this up into 5 subintervals, I'm going to do the same thing here, except this time, if I'm going from 2 to 3, and I want to make this into 5 subintervals, I need 4 tick marks. So 1, 2, 3, 4. They don't have to be exact. You're just trying to kind of get an idea of what your data points are going to look like. But notice now that you have 1, 2, 3, 4, 5 intervals inside this interval from 2 to 3. Now, this is 1 unit from 2 to 3. 1 divided by 5 is 1/5. Remember that you can always look at your delta x, which is b minus a over n, which in this case is 3 minus 2 over 5, which is 1/5. Now, the nice thing about working with 1/5 is it's a terminating decimal. Last time we were working with 1/3. 1/3 is not a terminating decimal. 1/5 is. 1/5 is the same as 0.2. So if you don't want to work with the fractions here and you want to use the decimal, as long as it terminates, that's fine. So you know that to get from one data point to the next, you're going to add that delta x to it. So 2 plus 0.2 gets you to 2.2. Add 0.2 to that and you get to 2.4. Add 0.2 to that and you get to 2.6, and then 2.8, and then up to 3. And verify that that makes sense. Some of you have just better number sense than others. We all have different strengths and weaknesses. But if you need to do a little bit more work on that, fine. If you're kind of like, yeah, big deal, I'm just going to write it down, no problem, fine too. Now, another nice thing about this is that since you're not working with fractions here and you have these nice terminating decimals, you can very easily get these midpoints. You know that halfway in between 2 and 2.2 has to be 2.1. So this is x sub naught, x sub 1, x sub 2, x sub 3, x sub 4, and x sub 5. And this guy right here is x sub 1 bar. And then in between x sub 1 and x sub 2, well, the in-between value there is 2.3. So you even have less work to do here for n equals 5 than you do with n equals 3. So you have more data points, but they're easier to obtain. 2.5 for x sub 3 bar. 2.7 for x sub 4 bar. And 2.9 for x sub 5 bar. And then you'll get used to using this midpoint formula, and you'll know that the last thing you need in order to complete this formula is the function values at those midpoints. So you're going to need f of x sub 1 bar, and that's going to be 1 over. In our case, our function is 1 over ln x. So our f of x of 1 bar here is just going to be 1 over ln 2.1. F of x of 2 bar is going to be 1 over ln 2.3, so on and so forth. You get the idea. Since I started writing them, I'm just going to finish it out. 2.5 and then 2.7 and 2.9. Now we're going to go through to find the approximation for the integral. We're going to take b minus a over n, which you already found to be 1/5. And then you're going to multiply it by 1 over ln 2.1 plus 1 over ln 2.3 plus 1 over ln 2.5 plus 1 over ln 2.7 plus 1 over ln 2.9. And that's it. So you can see how, depending on the type of number you're working with, this could be in a harder or an easier problem. Before I compute this value, does anybody have a question about how I obtained these numbers or any parts of this formula?
So I guess in a wider sense, when would we probably want to use this problem for, in general, or I guess, can we use it for anything?
I mean, in this class, you can't use it for anything except when I ask you to approximate, and I'm specifically going to tell you the rule to use. In general, it would be used anytime you can't figure out how to solve the integral, but in most cases, if you were working as an engineer somewhere, you're not going to be computing integrals by hand anyway. You're going to have computer algebra systems that will do that for you. So you wouldn't even be using these approximation techniques, assuming that you had some sort of computer algebra system. So it's really just sort of learning these techniques, whether or not you end up using a lot of them one day. I mean, I don't know. I've talked to some engineers who say that occasionally I actually have to compute an integral by hand, but most of the time I just use computer software. And that basically means that everything you're learning in this class it's good for you to know. It's important for you to, I mean, obviously know how to do this stuff if you're gonna, go off and do some sort of STEM job, but a lot of this type of thing you're not going to be doing on the daily. So, I mean, it's a good question, Greg, and unfortunately the answer that I have for you is probably not very satisfying, but it's just another one of those things in this class that you're learning that's good to know. You might use it one day, you might not, but whether or not you're going to eventually use it is not up to me. I'm just supposed to teach it to you.
Oh, well, no, I was just asking, like, we could use this for any problem integrating, I don't know, in Calc 3, if there's, like, if it's part of another problem to integrate something.
In Calc 3, I know from teaching Calc 3, it's been a while since I've taught Calc 3. I let my students use integration tables for everything. You might have a hard time fitting something to a table. I guess it depends on your teacher's comfort level with you using approximated values. If you're just trying to get close, if you're just trying to get an idea, then yeah, I would say that you could use this. Honestly, if I was teaching Calc 3 and one of my students had an integral they couldn't solve and did this, I would probably be just so happy that they remembered it and got close that I would probably still give them credit. It would just depend. There might be some teachers in Calc 3 who even let you use Maple in a computer lab on your exam, which is just a computer algebra system. I did not. My Calc 3 teacher let us use our TI-89s. I know most of the time nobody uses a TI-89 anymore, but it basically did integrals for you. But Also, that being said, remember how I showed you that you could graph this in your graphing calculator and you could actually find the definite integral from 2 to 3, and it would give you an approximated value that's actually closer than this. So yeah, technically, you would have to ask your teacher in Calc 3 about when using this would be appropriate. Are you any more satisfied with my answer now, Greg, or are you even more frustrated by it?
No, it's good.
Okay.
But with the tables, I guess.
Yeah, if you can't find it with the tables, this would be one of the options in your toolkit for how to get at least an approximated value. Yeah, technically, if you had to show your work and all you did was put it into your calculator and graph it and hit number 7 for the calculate, your teacher would be like, okay, where'd you get this? Like, where's your work? So, yeah. Yes. All right. Oh yeah, we got to put this in our calculators. I'm just going to enter this again. Sometimes I reuse my old formulas, but I'm just going to enter this again. So parenthesis, don't forget your outside parenthesis, otherwise your 1/5 won't be distributed. 1 divided by ln 2.1, don't forget to close that off, plus 1 divided by ln 2.3, close it off, 1 divided by ln 2.5, 1 divided by ln 2.7, 1 divided by ln 2.9. Now, if I got something that was really far off from what I got in the last approximation, I would look back and be like, whoa, did I enter something wrong? Because this should be at least close. And this is close. It is close. We're getting approximately 1.117161372. Now, remember that when n equals 5, you're dividing this into more rectangles. You're going to get a closer approximation to your actual solution. So if you were to round this to 4 decimal places, you'd be getting 1.1172. This is actually going to be closer to the value of the integral, which I found the actual value. I did this before class. 1.1184. So you can kind of see how we started off a little bit further away. We're at 115, and then we got closer with 117, and then the actual value is approximately 1184. So even just splitting this into 2 more subintervals got you a lot closer than you were with n equals 3. And this is another one where you could possibly see something like this on your test where I would ask you to use a formula from your table of integrals to do it. This is probably like right there in the table for natural log forms. I'm looking for it just because I feel like this form has got to be in there. Maybe you could use number 116 with n being -1. Maybe they stipulated you can't use n equals -1. But you would definitely be able to look back to your table if you were asked to do this in a table. Otherwise, you'd have to find another technique from the chapter, like parts or something. Okay, so that was the midpoint rule. I'm going to do the trapezoid rule next. It's a little bit easier to apply, I think. Let me show you a picture of what it looks like. Any questions on the midpoint rule before I do trapezoid rule? This picture is a little bit harder to see just because of the way they drew the trapezoids, but I still thought it was a nice picture. All right, this is upside down for me. Okay, so your trapezoid rule, your book lists it slightly different, so I would not write down this formula. You can if you want, but it's written slightly differently in your book. So I'm going to give you your book's definition. But what it does is instead of using rectangles and then talking about finding that halfway point between each rectangle, it splits this up into little trapezoidal segments. There's a proof in your book if you're interested in sort of seeing how this formula was developed. But each little partition here is a trapezoid, not a rectangle. So one would imagine that using the trapezoid rule would probably give you a closer approximation. I mean, maybe it would depend on the particular graph, but since you're allowed to have this slant at the top, I would imagine that you would get better approximations using the trapezoidal rule. So I'm going to give you the trapezoidal rule now. If a function f is continuous on the closed interval from a to b, then, and here's your formula, the integral from a to b of f of x dx is approximately equal to b minus a over 2n. Don't forget that 2 in the denominator. That's a change from the midpoint rule. And then you're going to multiply this by f of x sub naught. Already that's a little bit easier because you're not thinking about x bars. Twice f of x sub 1. And then twice f of x sub 2. And you're going to continue this pattern until you get to twice f of x sub n minus 1. And you're going to add that on the ends to just once f of x sub n. So the first and last term, you're only going to just use the function value. And then for all the terms in the middle, you're going to multiply the function value by 2. And of course, this means that you're splitting a to b into n subintervals, where n is the number of subintervals okay, the subintervals you kind of know already, but okay, I'll write them down again just because maybe they'll be helpful to you. You're going from x sub naught to x sub 1, x sub 1 to x sub 2, so on and so forth until you get to x sub n minus 1 to x sub n. Each of width delta x equals b minus a over n. So that is the same. So just taking the difference between a and b and subtracting by the number of subintervals. And that's it. So now we're going to do example 2. Use the trapezoidal rule. to approximate. And now I'm going to give you an integral that we can easily find without approximating it. And then you can get a good idea of how close we are. So we're going to approximate the integral from 2 to 4 of x squared dx. And we'll just use n equals 4 subintervals. Do an even number this time. Just like with the midpoint rule, I would suggest, you don't have to, but I think it's an easy visual if you kind of just draw your, what would be on your x-axis. You're going from A to B, which means you're going from 2 to 4. And if you're looking for n equals 4 subintervals, then you're going to use 3 tick marks. So you're always going to take n minus 1 to figure out how many tick marks you need to place inside your interval. So we'll go with 1, 2, 3. Now, most of you are going to eyeball this, and that's why I like to draw this out in number line style. And you'd be like, wait a second, the middle one would have to be 3. Therefore, the first tick mark would have to be 2.5. The third tick mark would have to be 3.5. Yes. If you did not draw this out and you cannot easily eyeball it, then you would just do delta x equals b minus a over n, which is 4 minus 2 divided by 4. 4 minus 2 is 2, divided by 4 is a half. So this is just the value that you're going to add to each tick mark and to get to the next one. So 2 plus a half is 2.5. We kind of talked last time about how it's actually easier to use decimals in this case if they're terminating. So you might want to just go with 2.5. It'd be easier than using 5 halves. The last thing you want is to have to enter more fractions into your calculator and introduce places where you would need more grouping symbols. Add a half to that and you get to 3. Add a half to that and you get to 3.5. Add another half and you get to 4. So double check and make sure that you've completed this and that each interval has the same width. Okay, so I'm going to go back to the definition here for the trapezoidal rule. We're going to take b minus a divided by 2n, and we're going to multiply it by f of x sub naught plus twice f of x sub 1 plus twice f of x sub 2, so on and so forth. If you want to just evaluate your functions inside the formula, that's fine. If you're one of those people who likes to evaluate them outside the formula, that's also fine. You have x sub naught, x sub 1, x sub 2, x sub 3, and your last data point is always going to be the nth data point. So make sure you're not starting on x sub 1, but you're starting on x sub 0. So if you were looking for f of x sub naught, that would be f of, in our case, f of 2. And remember that your function is inside the integral, x squared in our case. So f of x is x squared. Therefore, f of 2 would be 2 squared, which is 4. F of x sub 1 would be f of 2.5. Now, if you find this to be easier using fraction, fine. If you want to use the decimal, also fine. You decide. And then 2.5 squared as a decimal is 6.25. I know some students like to do everything inside the formula. Others like to have everything laid out and then put it in the formula. So I'm just going to piece all the information out separately and then we'll put it together. You know, that's up to you. You'll get into a rhythm as you go through your homework. F of 3 is 3 squared, which is 9. F of 3.5 is 3.5 squared, which is 12.25. And then f of x sub 4 is f of 4, which is 4 squared, which is 16. And of course, verify, make sure your answer makes sense, that these values, you're squaring them. They should continue to get larger as you work your way through. And then we'll apply the formula. So I'm going to take b minus a over 2n. So b minus a for us, actually, let me go from 2 to 4 of x squared dx is approximately equal to b minus a over 2n. N in our case is 4. We split this up into 4 subintervals. Then we'll multiply that by, inside the formula, f of x sub naught plus, and then everything that's inside these terms is going to get multiplied by 2. It's only the first and last terms that don't get multiplied by 2. So for the first term, we're just looking at f of x sub naught, which is 4. And then we'll take twice f of x sub 1, twice f of x sub 2, twice f of x sub 3, and then once f of x sub 4. So there are benefits to doing it this way where you've already listed everything out and you're putting more simplified versions in here. The only downside I could see to that would be maybe if you computed this incorrectly, then everything would be wrong inside here. I guess the reason I think it might be more helpful to do this separately is because you're just putting fewer grouping symbols into your calculator. Otherwise, you would have been going 4 plus 2 times parentheses 2.5 quantity squared, close your parenthesis. See what I'm saying? It just leaves more room for having calculator errors where your math might be right. And on a test, that's fine. I can see your work and I can see that you correctly had it laid out. Maybe you put it in your calculator wrong. That happens quite a bit. But on Achieve, you'll keep getting the wrong answer and you'll be like, why? What's happening? And it really turns out that your formula was right. You were just not entering it into your calculator appropriately. So be careful with that. 4 minus 2 is 2 divided by 8. 2 over 8 is 1/4. And then, I mean, it's kind of up to you how you want to find the rest of this, but I will show you my screen. Let's see, 4 plus 2 times 6.25 plus 2 times 9 plus 2 times 12.25 plus 16. And that is 75. Double check, double check. 16. Okay. So 1, 2, 3 terms being multiplied by 2, and then divide that by 4 or multiply it by 1/4 if you want to think about it that way. And you should get 18.75. So this is the n equals 4 trapezoidal approximation. Questions about the approximation first? So for this example, I gave you a function where you could already integrate it. You're going from 2 to 4 of x squared dx. That's 1/3 x cubed from 2 to 4. So that's 1/3 times 4 cubed is 64. 2 cubed is 8. So 64 thirds minus 8 thirds is 18.6 repeating. It's also the fraction 56 thirds. So this is the exact value, the actual value of the integral. I just gave you a simple one here so that it's something that you're familiar with. You can check it. Also, nothing that would, cause us a lot of crazy arithmetic problems with the example. Okay, but you can see how close it is. And if you wanted to play around with this a little bit, you could even do, another set of subintervals. You could split this up into 8 subintervals instead of 4. And, that would be a little bit easier to work with too, because you would just be getting midpoints at that point, and then just sort of working with including those midpoints into your calculation and see how much closer you can get to the actual value. So just to give you an overview, the error piece that I decided not to include because I was worried about your achieve homework and you not being able to get the right decimals. Let me give you an example of what the formula is. Because you first look at the formula and it's just like, yeah, no big deal, easy, got it. But it actually is kind of hard to work with. I'll show you what it is just so that you can say you've seen it, even though you don't have to use it. Let me flip my, oh, I don't have to flip, never mind. I'm on the right side of the page. For the trapezoidal rule, what you're looking for is you're trying to find the error given a specific value. The problem with this is not the A and the B and the N, it's the M. M is the absolute maximum value of the absolute value of F double prime. Now, in order to do that, you have to go back into your Calc 1 toolbox, thinking back to what you did in applications of integration in Chapter 4. Not only do you have to find the first derivative of F and the second derivative of F, but then you have to look at the absolute value of that graph over this interval, and you have to isolate a value that's the absolute maximum value. Now, that seems like, okay, not a big deal, but most of these absolute maximum values that you're going to see in the problems in your text are not going to be nice integers. They're going to be something like 0.734. And then you have rounding issues then, depending on what you allow your M to be. That was the issue that I was running into with that. If you find this interesting and you're kind of like, oh, let's go through and look at the error in the approximation and see how close it is and figure out how many subintervals would need to split this up into in order to have an error that's less than 0.0001. Be my guest, go ahead. I'm not going to talk about this. Like I said, I don't even usually cover this section at all. Sometimes I do, sometimes I don't, depending on how much time we have. But the error, if we were in person, I would have just covered this. But with Achieve, it just I couldn't get it to properly to make me feel good enough about it that you guys were gonna not run into a bunch of approximation issues in your approximating section. Okay, so I'm not going to show any more examples for the trapezoidal rule. I'm going to show you Simpson's rule. I feel like once you've done one of these, it's pretty straightforward. You know how to use the formula, you know how to find the parts, and even just having done the midpoint rule, I feel like you had a better understanding of how to apply the trapezoidal rule because they kind of use the same components. Simpson's rule, I have a picture of that I'm going to show you. Oh, so many books. The problem is I'm on the textbook selection committees, so they sent me all these books, and technically you can recycle them when you're done. Of course, I keep them because when it comes to math books, specifically calc books, I like to have a stash of them. It's always really nice to be able to see different perspectives on things, and my husband goes crazy. It's just like, why do we have like 15 calc books in here? And then the book I used to teach out of, I own in like 4 different editions. So he's just like the 8th, the 9th, the 10th, the 11th edition. Like, why? You guys, it's a problem. You don't have this problem. Most of you are like, whatever, ebook. It just takes up a lot of space. All right.
I have the same thing. I have like 3 different versions of my discrete structures book for computer science.
Do you ever look at them?
Oh, yeah.
Okay. I look at mine too. My husband's like, you don't even use these. And I'm like, that's not true. I use them all the time. Just because you don't see me using them. Husbands, man. All right. I'm glad someone understands me, Becky. All right. This is see, yeah, you get it. This is the picture for Simpson's rule. It's presented slightly differently in your book, so I'm not going to give you that particular definition, but this picture I thought was pretty good. It basically uses parabolas instead of rectangles and trapezoids to approximate pieces of the curve. Now, Simpson's rule is generally used more often with super wavy functions, maybe functions that oscillate like trig functions, some sort of sine or cosine. You're going to maybe think that Simpson's rule will give you a closer approximation just because of the fact that it's approximated using parabolas. And again, this is something where your book derives the formula for it. It is interesting if you wanted to see it. I just need to know that you can use the formula and approximate the integral and just kind of understand the idea behind it. So without further ado, I will give you a definition for Simpson's rule, and I'll give you an example of how to use Simpson's rule, and then we'll be done approximating integrals. I'm too zoomed in, that's the problem. Simpson's rule, your last one. If you were wondering, this is the last one. Oh, if a function f is continuous on the closed interval from a to b.
You're upside down.
Oh, still, thanks. It's like every picture I want to show is on the other page, and then I have to flip. Thanks, Becky. For f continuous on the closed interval from a to b, we have the integral from a to b of f of x dx being approximated by b minus a over 3n. So we've sort of built these up so that each time we're including another multiple in the denominator. All right, so this one is slightly trickier, not any trickier than the midpoint, but you gotta follow your coefficients here. So you're going to start out with f of x sub naught. And you're going to add that to 4 times f of x sub 1. And you're going to see there's a pattern here, so it's not too bad. But then you're going to go twice f of x sub 2. And then 4 times f of x sub 3. And twice f of x sub 4. And then dot, dot, dot. So you're going 1, 4, 2, 4, 2, and then you're going to work your way backwards in the opposite direction. So it's going to be twice f of x sub n minus 2 plus 4 times f of x sub n minus 1 and then 1 time f of x sub n. So 1, 4, 2, 4, 2, 4, 1. So we have to be partitioned into an even number n of subintervals in this case. They have to be even so that we have this behavior where we have the symmetry going on with our formula. Each of width b minus a over n. So same idea there.
So is x n minus 2, are those, for n minus 2 and n minus 1, are those coefficients always going to be 2 and 4? Or do we follow the 4, 2, 4, 2, 4, 2 pattern along until we hit the end?
So you're always going to work outside in. So, and I'm going to give you an example of this so that you can see. Let's see, my example is going to be using, hold on. I believe I'm going to be, oh yeah, so my example is going to be using 4. So I'm going to show you how it works with 4. But yeah, you're always going to be going 1, 4, 2, 4, 1, depending on how many intervals you have. So that will be in the example that I'm going to be doing, because I'm going to be splitting this up into n equals 4 subintervals, which means you're going to have 5 data points. So 1, 2, 3, and then the last 2 will be these 2. So you're going to see that they'll always work their way out symmetrically, because you're always going to have an even number of data points. So like, let's say if you had n equals 6 for your partition, then you're going to have 7 data points. Then you would go 1, 4, 2, 4, 2, 4, 1. See what I'm saying? So basically your first and your last are going to be these 2. And then your second and your second to last will be these 2. And then your third and your third to last will be that one. And then you sort of work your way in. But it's always going to work.
Okay, and then just stop when you hit the middle.
Yeah, stop in the middle. Exactly. Because you're using even subintervals, you're always going to be able to have that symmetry where you're just going to have that value in the middle.
Gotcha. Okay.
Yeah, good question. But yeah, this will always work out so that you just sort of, I was going to say it's like a telescoping series, but we're not going to be talking about that until next week. So we'll sort of revisit this idea when we talk about telescoping series. But yeah, I know, I kind of wish I had this on one line, but you're working your way from the outsides in. Okay, so let me, any other questions on this before I give you an example? The pattern's different, but I mean, if you want, we can even add another example, maybe where we do 8. Some of you were like, no, I have an example with 8. You don't. We could always add one in the office hour if you would like. Do one with 8. Or we could do one with 6. You just let me know. I do have one prepared if you want to see it in the office hour. I don't really feel like it's necessary to add it into class, but if you want to see more, absolutely. Example 3, use Simpson's rule to approximate. I'm going to give you a trig function here. This is going to be the integral from pi over 2 to 5 pi over 2. Oh, you know what? Now I kind of feel like the other one might be better. No, never mind. This is a better one to do. We'll do this one. Pi over 2 to 5 pi over 2 of sine x over x dx. This one's good, actually, just because of the values of a and b. More instructive, I guess. You know what we could do, though? We could do it for n equals 4 and n equals 6. I'm going to do it for n equals 4. If you want to see it for n equals 6, stick around for the office hour. Optional, of course. All right, so we are going from A to B. I really like using this number line kind of thing. I'm going to try to space this out a little bit more because I've been crunching these together and running out of space. So I'm going to start at the lowest endpoint with pi over 2, and I'm going to go up to 5 pi over 2. Now, if n equals 4, that means I'm going to need 3 tick marks. They don't have to be even, just put 3 in there so you can see that you have 1, 2, 3, 4 subintervals. When I said they don't have to be even, I meant they don't need to be evenly spaced. You know, do the best you can. Of course, n has to be even. Now, if you are thinking about this in terms of numerators and denominators, you might find it easier to eyeball this versus using a formula. Or you could use the formula and determine that the width of each subinterval is b minus a over n. You can do that too. B minus a is 5 pi over 2 minus pi over 2 divided by 4. And some of you will do both just because you want to verify, and that's fine. Never hurts to do a little bit more. 5 minus 1 is 4. So 4 pi over 2 divided by 4. So when you're dividing by 4, you're multiplying by 1/4. And you're getting delta x equals just pi over 2. So 4 pi over 8 is pi over 2. You can also think about it that way. So that means you're always going to be adding pi over 2 to get from one interval to the next. So pi over 2 plus pi over 2 is just going to give you 1/2 plus 1/2 is 1. Plus pi over 2, so 1 plus 1/2 is 3/2. Plus another 1/2, and you'll get to 4/2. So 4/2 pi, 4 over 2 is 2, and then another 1/2 gets you to 5/2. If you were just looking at denominators, you could have come to the same conclusion. You would have said, okay, these are my endpoints. They both have a denominator of 2. This numerator is 1, that one's 5. The number that's smack in between 1 and 5 is 3. So the middle must be 3 pi over 2. And then if you remember your trig really well, then you'll just remember that right in between pi over 2 and 3 pi over 2 is pi. And, you know, in between, you've got this situation again. Or you could, you know, equate denominators again. So what's in between 1 and 3? Well, it's 2. 2 pi over 2 is pi. In between 3 and 5, you have 4. 4 pi over 2 is 2 pi. So you've got a bunch of different options for how to split these up. If you want to be very precisely mathematical about it, you can always use this formula for delta x. But this is your x sub naught, x sub 4, x sub 1, 2, 3. And now you just need those function values. Since you're not going to be able to get actual, well, actually you can for these get nice function values. Never mind. I will find the function values separately. I was thinking that these were going to be weird values for which you would not be able to evaluate sine x over x, but these are really nice, nice angles here. All right, so let's first find f of x sub naught, which is f of pi over 2. So we're doing this times sine x over x. Sine pi over 2 over pi over 2. Now, again, you could put all this in your formula. My only fear is that you might have too many grouping symbols, put this into your calculator wrong if you don't sort of split this up into parts. Sine pi over 2 is 1. 1 divided by pi over 2 is 2 over pi. And then do the same thing for these other values. We'll next look at f of pi. Sine pi over pi, well, the nice thing about that is you don't have to worry about putting this whole clunky thing in your calculator because the sine of pi is 0. And 0 over pi is 0. Oh, sorry, I wrote f of x sub naught, but that was definitely f of x sub 1. F of x sub 2 is f of 3 pi over 2. This is going to be the sine of 3 pi over 2 divided by 3 pi over 2. The sine of 3 pi over 2 is -1. When you simplify this, you're going to get -2 over 3 pi. For x sub 3, you're going to have f of 2 pi. The sine of 2 pi is 0. Divided by 2 pi is still 0. And then for your last data point here, for your end point, you're doing f of 5 pi over 2, which is just coterminal with pi over 2. If it's coterminal with pi over 2, well, the sine of pi over 2 is 1. The sine of 5 pi over 2 would also be 1. We'll get 2 divided by 5 pi. So 2 of these data points, we can enter as 0 just so that we can show them as placeholders in the formula, but they're not actually like major quotients that we have to enter into our calculator. Any questions so far? Okay, so let's start putting this together then. Our integral is going to be from pi over 2 to 5 pi over 2 sine x over x dx. Look at that, I put my dx in the denominator. Talking and writing. I know that's my job, right? Talking and writing. Sometimes it goes smoothly, other times not so much. B minus a divided by 3 times n. Okay, we'll simplify that in a second. We might as well look, I simplified everything else. I'm actually going to do this off to the side because now it's bothering me. B minus a over 3n is going to be 5 pi over 2 minus pi over 2 divided by 3 times 4. 5 pi over 2 minus 1 pi over 2 is 4 pi over 2 divided by 12, which is 4 pi divided by 24, which is pi over 6. So I'm just going to write this as pi over 6. The last thing we need to do is enter this in our calculators. That'd be a nightmare. By the way, notice that I kept these exact values for now. We're going to approximate this at the end. You want to be careful not to make all these little in-between approximations. So yeah, you might technically be like, well, sine pi over 2 over pi over 2, and then you would approximate this to some decimal that's a little bit less than 1. Just leave it exact when you enter it into the formula. When you get your final answer, that's what's approximated. The last thing you want to do is have these stacking decimal issues that end up giving you an answer that's too far off to be accepted. You'll have to work with that tolerance and see what it gives you. I don't know how tolerant it's going to be. So keep everything exact until the end. All right, so we're doing pi over 6 times f of x sub naught, which is 2 over pi. All right, so now I'm taking you back to your formula here. There it is. Okay, so this will be for our x sub naught, x sub 1, x sub 2. Our x sub 3 is going to be this value, f of x sub n minus 1, because n is 4. So if n is 4, f of x sub n minus 1 is f of x sub 3. So this will be our f of x sub 3. This will be our f of x sub 4. So we're doing 0, 1, 2, 3, 4. So our coefficients will be 1, 4, 2, 4, 1. So they'll work their way inside. They'll be symmetric from the outside in. Okay, so f of x sub naught was 2 over pi. Then we'll do 4 times f of x sub 1. Well, that's just 0. Twice f of x sub 2. F of x sub 2 is negative 2 over 3 pi. Then we're doing 4 times f of x sub 3, which is again 0. And then 1 times f of x sub 4, which is 2 over 5 pi. These trig ones are just a little bit harder because not only are you splitting things up into these integer multiples of pi or pi over 2, but you have to also know your trig values. I mean, I guess technically if you just put the whole thing in your calculator, it would do that for you. I might write that out just so that you can see what it would look like, because that is technically an option if you entered it like that. It would just be a lot of grouping symbols and a lot of things could go wrong. That's why I didn't do it that way. But now at this point, you can put this into your calculator. So what you're entering is pi over 6 times 2 over pi minus 4 over 3 pi plus 2 over 5 pi. That's what I'm going to be entering into my calculator. And we're going to get our decimal approximation here. Don't forget to use the actual pi button. Don't use 3.14. You're going to approximate that not closely enough. So pi over 6 times parentheses 2 divided by pi minus 4 divided by. Now, listen. This is where you need to be really careful. Sorry, I'm not trying to be a jerk, but I'm trying to get your attention. I always learned when I was in methods teaching school that sometimes if you're trying to emphasize something, you gotta change your inflection. This is important. When you divide by 3 pi, don't do this. This is one of the most common mistakes when entering expressions having to do with pi into your calculator. You know what this is doing? This is taking 4, dividing it by 3, and multiplying 4/3 by pi. That's not what you want. If you're dividing by 3 pi, you must put parentheses around your denominator. Otherwise, it doesn't know. It's going to apply order of operations for multiplication and division from left to right. It doesn't know that you want 3 pi as a group. It doesn't know that unless you force it to do that. Be careful. Plus 2 divided by, and I'm going to do the same thing for 5 pi. I got to put that whole quantity in parentheses. I'm going to close that off again. This is what it should look like in your calculator. 2 over pi minus 4 divided by the quantity 3 pi plus 2 divided by the quantity 5 pi. And you're going to get an approximation of 0.17. Technically, it's going to be 0.17 repeating. If you are asked to approximate this to 4 decimal places, it'll be 0.1778. So you can do that. This is another thing that you could even just verify in your calculator using the graph and then number 7, calculating the definite integral for the area under the curve. And just see, make sure you're close. Okay. Okay, that's all I officially have for you tonight. If you would like to see me put this whole unsimplified expression into my calculator and what that would look like, ask me in the office hour. If you want to see this for n equals 6, stick around for the office hour. If you have any other general questions, stick around for the office hour. As I mentioned previously, I'm going to have a very short presentation for you asynchronously on 7.8, which is about using tables of integration to actually find the values for integrals. I'm not going to give you anything crazy in there. It's basically just like, can you use the tables? That's it. That is all. I'm going to have that available for you by Friday morning. It'll be short, so hopefully everything will upload quickly. I'll probably be recording it tomorrow during tree school because that's my life. But other than that, stick around. I'll be on for another like 28 minutes if you have questions. Test on Wednesday, the 20th. That is all. There's homework for you on Achieve. Enjoy. I'm going to keep this recording going, but I didn't know what kind of questions you guys had, if anyone was going to stick around. Let me know.
I had a quick housekeeping question.
Yes, go ahead.
I was late today because I was finishing up my midterm for CIS. So is there any chance I can do the quiz after class? Like right now?
No, the quiz cannot be done after the fact.